Hello. In this video, we are going to look at complex roots of the characteristic equation. And in particular, what we're looking at is, suppose we have a homogeneous linear second order differential equation and that differential equation has constant coefficients and we go through and form the characteristic equation, and that characteristic equation has complex roots. So what are we talking about here? So we're talking about a second order differential equation. It's linear and it has constant coefficients. That's our setup. And we go through and we form the characteristic equation, which is how we solve these. And when we solve the characteristic equation, we get complex numbers. Okay, so what do we do with these? Well, we can still rely upon our information from the last video, which says that if we have two roots to the characteristic equation, we can take those roots and just plug them in as exponents to an exponential function, and those will solve the differential equation. So that's still okay. You can just take this and do alpha plus beta I times t, which is, again, this is what we did in the last section, except we had two real roots, not complex roots. But the idea can be extended. Okay, and so if you just take the two roots that you end up with a characteristic and you just pop them in as exponents, that still will work. If we took these and plugged them in to the differential equation, it would give you a true statement. However, the problem is that we started with a differential equation that was defined for real numbers, and we ended up with solutions that have complex numbers in them. And so we would really like to go through and find a way to convert those. So can we convert these solutions into an alternate form without complex numbers? And that's going to be our goal. So let's see, how can we accomplish that? All right, so to go through and do that, what we're going to start off by doing is proving a theorem. All right, so given y double prime plus p of ty prime plus q of ty equals 0, where p of t and q of t are both real valued functions. So not complex, no complex numbers here, where p of t and q of t are real valued functions. And then if y equals u of t plus I times v of t is a complex solution, then both u of t and v of t are individually solutions to the differential equation. Okay, so I like this proof. It's this theorem. It's a fairly simple theorem, and I like the proof. It's a very simple proof. So what does this say? It says that if we have a second order differential equation, this one does not have constant coefficients, but it's second order, linear, homogeneous. If you have a differential equation that has that form, and there's no complex numbers in it, it's all real valued functions, and yet somehow you have a complex solution. So this we're just assuming that this does, if you plug it in, it does work. Where does that come from? It doesn't matter. Just suppose there is a complex solution that does work. If that's possible, then the result of that is that the individual parts of the complex solution have to work. So the way that complex numbers work is you have a real part and you have an imaginary part. So the real part has to solve the differential equation individually alone, right? So without the complex part, and the complex part also, if you plug it in, has to solve the differential equation as well. So if this is true, if this makes the differential equation true, then both of these individually make the differential equation true. So how do you go through and prove it? This is a lovely simple proof. It's a direct, straightforward. If this is a solution, that means if you pop it in, it has to work. So let's just pop it in there. All right, so what's going to happen? We're going to get u of t plus I v of t, right? So that's what y equals. So we're going to have that double prime plus p of t times u of t plus I v of t prime plus q of t times u of t plus I v of t. And that has to equal 0, right? Because we're just taking everything and popping it in here, and it has to be true. All right, so derivatives. How do derivatives act over addition? They distribute. And so we can go through and rewrite this. This is going to be u double prime of t plus I v double prime of t. And then here, again, the derivative is going to distribute. And then I'm going to also distribute the p of t at the same time, just for simplicity's sake. So we're going to get p of t u prime of t plus p of t I v of t prime. And then we'll just distribute here too. So we're going to get q of t u of t plus q of t I v of t. Okay. And then the next step, we're going to go through and we're going to split these things apart. We're going to get the u's together in one area and we'll get the v's together in another area. So we're going to have u double prime plus p of t u prime and then plus q of t u of t. And then let's do the v's next. So we're going to have I, and we can factor it out. Like, so if you look at the v's, you've got an IV double prime, you've got an IV prime, and you've got an IV. So we can factor out the I, and we get v double prime of t plus p of t v prime of t plus q of t v of t. Okay, so now if you look at this, right, and as two separate parts, we have a real part that's here. So if you go through and multiply all this out, collect all this stuff, you're going to get a real number out of this. And then that's plus I times an imaginary number. Well, not the imaginary part, right? So the imaginary part, the I is the imaginary number, but you're going to have times the imaginary part. And so going back to complex numbers, if you have A plus BI equals 0, if you have a complex number that has that form, the only way that that can equal 0 is if A equals 0 and B equals 0. That's the only way that's possible. There's no way for A and B to cancel each other. These are like two separate parts. And for the two separate parts to equal 0, A itself has to be 0. If A is not 0, then you can't end up getting 0 out of this because the B can't cancel that A. And then the same thing goes for the B part. If you had a 3 here, there's no way for the A to cancel the 3. And so both parts have to equal 0. And so now once we've gotten into this form that has that A plus BI form equal to 0, so that tells us that U double prime of t plus P of t U prime of t plus Q of t U of t equals 0, and V double prime of t plus P of t V prime of t plus Q of t V of t equals 0. And thus, if you take a look at this, what does it mean to be a solution to this differential equation? It just means that you plug it into this and it makes it true. Well, if you compare these two, you can see that we have just substituted U of t for y. So thus, U of t is a solution to the differential equation. That looks like more like an N than a U. Let's try that again. U of t is a solution. All right, and then how about this one? Take a look at this, compare it. They look exactly the same, except you've replaced y with v of t. Thus, v of t is also a solution. And that completes the proof because that's what the theorem says. So the theorem says that if you have a complex solution, then out of that you can end up saying the individual parts themselves are also solutions, which is what we showed. We showed that if u plus iv of t is a solution, plug it in, it works, then the consequence of that is that u of t itself and v of t itself has to be a solution as well. Okay, so we are going to need that. And then while we're at it, let's go through and derive one more thing. Let's go through and derive Euler's formula. So what Euler's formula says is that e to the it equals cosine of t plus I sine of t. So that's what it says. That's what we want to go through and show. The way in which you show this is you start off, you can go through and, so this we're going to actually go through and use our Taylor expansions, our information from Calc 2 on series and sequences. We're actually going to use it. So we're E of t, if you recall, the Taylor expansion for E of t is the summation n equals 0 to infinity, and we get t to the n over n factorial. So that comes right out of Calc 2. It's the last section, I think, in that chapter on series and sequences, which is so fun. All right. From there, what you can do is we're just going to substitute an it in place of the t. Right. So if e to the t equals this, then we can put something in place of the t, and it would put something in place of the t on the other side. And so when you do that, you're going to get the sum n equals 0 to infinity, and we're going to get it to the n over n factorial. And then from there, you can go through and rewrite that. So the n is going to apply to both the variables here. So we're going to get n equals 0 to infinity, and we'll get I to the n, t to the n over n to the factorial. And then what we can do is we can write some of this out. So if n equals 0, so I to the 0 is 1, t to the 0, 1, and 0 factorial 1. So we start off with 1. And then if n goes to 1, then we're going to have I to the first, t to the first, 1 factorial. So that's going to be plus ti Okay, and then if n goes to 2, now we have I squared. I squared is -1, so we're going to have a negative, and then t squared over 2 factorial. And then if n goes to 3, we'll have I to the third. I to the third is negative I, so we're going to have a negative t to the third I over 3 factorial. And by the way, what I'm using there, if this is if it's been a while for you, so I equals the square root of -1, so I squared equals -1, I cubed equals negative I. Hold on, my brain broke there for a moment. So we've got I squared times I, so that's going to be negative I, and then I to the fourth. You're going to end up back at 1. Okay, so how do you get 1 out of that? So it's you have I squared times I squared, which is -1 times -1, which equals 1. And then I to the fifth is back to I. Okay. So anyway, it's just a pattern that you end up with here, where if you have I to the first, that's just defined to be the square root of -1. If you square it, you get square root -1 times square root -1, so that's -1. And then the rest just kind of follows from the pattern of pulling out squares as -1s. And so from there, we can, so just continuing here, so that's where the, where when I got to I squared, I put a negative sign, and when I got to I cubed, I went and did negative I. All right, so anyway, so now we're up to n equals 4. N equals 4, we're at I to the fourth, so that's going to be back to plus. We got t to the fourth over 4 factorial. And then the next one is going to be plus, and you can kind of just see a pattern at this point. T to the fifth I over 5 factorial minus t to the sixth over 6 factorial minus t to the seventh I over 7 factorial. And it just kind of continues from there. All right, so what we can do here is we can go through and split these apart based upon the I. So we're going to grab the even, the terms that have even t's. So I guess that's not the even terms, the first term, third term, fifth term, seventh term. And we're just going to grab those, and we're going to represent them as, let me try that that summation symbol again, because that was a disaster. So we get n equals 0 to infinity. That's going to be -1 to the n times t to the 2n over 2n factorial. Okay, and so what we're doing there is that we're just recognizing a pattern, for the terms. So the first term is positive, the second one's negative, then positive, then negative. So they alternate signs. That's why you put this -1 to the end. So all this is stuff that if you did it right after you covered series and sequences back in Calc 2, you'd remember better. But the -1 to the n is just the piece that you put in there to create alternating signs. We want to start with a positive sign. That's why we start with n equals 0. And then the exponents, so the first one has, 0 for the exponent, then 2, then 4, then 6. That's why 2n. And then the denominators, you could think of the denominator here as 0 factorial. 0 factorial is 1. So you get 0 factorial, 2 factorial, 4 factorial, 6 factorial. And so you get the 2n factorial. And so you can see that this term, this term, this term, they all turn into this summation. And then we're going to create a second summation where we go through and take I guess it's the even terms, but it's the terms that have the odd exponents for t, or I guess it's the terms that have the i's in them also. And so we're going to factor out the I, and we can represent those with n equals 1 to infinity. And then we get -1 to the n minus 1 times t to the 2n minus 1 over 2n minus 1 factorial. And you can check those as well. So why is it n minus 1 here? Well, we still have alternating signs. It goes positive, negative, positive, negative. But the thing is that, we're starting off with t to the first. And so that's why we're starting off at n equals 1 instead of n equals 0. And because it starts off at n equals 1, you need to shift the exponent here so that you start off with a positive. Otherwise, you'd start off with a negative if you just left it as n. And you get that. All right, so that's kind of neat that you can go through and take this and rewrite it like that. And now here's what's really cool, though. And again, this is something you'd have to go back and review your notes from Calc 2 from forever ago. But this guy right here is the Taylor expansion for cosine t. This guy right here is the Taylor expansion for sine t. And so we can go through and use our Taylor expansion for e to the t, manipulate it into the two pieces, and then end up getting using the Taylor expansion for cosine and sine to turn them, to get rid of the series, right? So you start off with e to the t, you turn it into a infinite series, and then you go through and break it apart into two infinite series, and then you shift back by going through and using the Taylor expansion again at the end. And the net result here is that e to the it equals cosine t plus I sine t, and that is called Euler's formula. That is a very cool. I guess that's a proof. That's a cool proof. So we got two proofs, not theorem, sorry, Euler's formula. Okay, so how do we go through and use these two proofs to get rid of our, to get rid of our complex numbers, right? So let's go ahead and just grab our first solution here. Y1 is e to the alpha plus bit plus bi plus beta I. E to the alpha plus beta I times t. That's y1. All right, so what we can do is we can go through and we can rewrite that. We can distribute the t here. So we're going to get e to the alpha t times e to the beta I times t. This one stays as it is. Here, you've got e to the beta it, so we can go through and use Euler's formula. Euler's formula says that e to the it equals cosine t plus I sine t. If you add a number next to this t, then that number is going to be added next to the t inside of here, right? So if we had a number next to the t here, it would be next to the t here, it would be next to the t here, here, all throughout, right? So you could just substitute. So essentially the beta just jumps in front of the t's. So we end up with cosine beta t plus I sine beta t. And then at that point, we could go through and we could distribute this. We get e to the alpha t cosine beta t plus I e to the alpha t sine beta t. And if you take a look at that, what is that? So what we now have is we have the whole point of this, y1 was a solution to the differential equation, right? If you go all the way back, what is y1? Y1 is what came out of the characteristic equation. And using our knowledge from the previous video, we know that anything that comes out of the characteristic equation, if you take it and plug it in, it will work, right? So you could take this and just substitute it in here and it will solve the differential equation. So if this solves the differential equation, then this solves it, then this solves it, then this solves it. And look at that, we have a complex solution to the differential equation. And what do we know about complex solutions to the differential equation? Right, well, we went through and we proved that if you have a complex solution to the differential equation, then each part, both the real and the imaginary part, are also solutions. And so we have a real part, we have an imaginary part, and thus each one individually is a solution. So we're just going to go through and split this up and say y1 is e to the alpha t cosine beta t, and then y2 equals e to the alpha t sine beta t. We can effectively just get rid of the I here and say that we've got these two solutions. Now, if you recall back in the last video, when we had two solutions to the differential equation, we went through and we took linear combinations of them I don't know if I used that terminology. I might have went through and said, you could put a C1 here, you could put a C2 here, and then we can add them. But that's actually, if you put that together, that's actually called taking linear combinations. So if we go ahead and do C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t, taking these two individually and writing them this way, this is called a linear combination. We're taking a linear combination of y1 and y2, right? And so when we were done going through and taking the linear combination in the previous section, we said, hey, we're good, we've got the solution. So we're going to do the same thing here and say, hey, we're good, we've got the solution. Now that might seem questionable, and if you're skeptical of it, that's good, so we're going to revisit that in a future section and prove that this is sufficient, that this is the answer, that we don't need anything more to it. But skepticism is good. It's good to be skeptical, so for one thing, what about this second solution? Well, the second solution, you'd have to go through and derive the formula for the negative part of Euler's formula, and I'm not going to bother to do that, but it's similar to this. And then you can go through and go through a very similar process to what we did right here. And if you do that, guess what happens? You get these two solutions again. Okay, so the second solution produces these two again. And so you don't get anything new out of the second solution. So that's why I'm not going to go through and go through the same process with it. But yes, it's very good to be skeptical that this is sufficient and that this is going to be the solution to differential equations that have that have complex roots. But it is, and we will come back and revisit this in a future video and prove that it is sufficient. All right, so instead, what we're going to do for this video, though, is we're just going to box this off and say, the end, this is the formula that you end up with when you go through and solve a homogeneous linear second-order differential equation with constant coefficients that have complex roots. Okay, so did you follow that? All right, so if you start off here, you form the characteristic equation, you solve it. That solution, that tells you that this is going to be a solution to the differential equation. That guy's transposed here. Then we can rewrite it like this, then use the theorem, then split them apart, and then we get to here. And so this is going to be the solution. Actually, hold on, but erase the y1 here. That is going to be the solution to the differential equation. And we're going to just move forward with that fact. Okay. So next, the thing that remains to be done is to go through and look at some examples. Suppose we want to go through and solve the differential equation y double prime plus y prime plus 9.25y equals 0. All right, so to go through and solve this, the first thing that so again, this is a homogeneous linear second order differential equation with constant coefficients. The way that you solve those is you form the characteristic equation. So we get r squared plus r. 9.25 is 37 fourths. Not y, sorry. 37 fourths equals 0. So there's our characteristic equation. To solve the characteristic equation, we go through and use the quadratic formula. So we get r equals negative b plus or minus square root b squared minus 4 a and then c all over 2a. And then if we simplify that, you get negative 1 plus or minus square root. What have we got here? This is 1 minus 37. So we're going to get negative 36 over 2. So let's actually go this way so we have some room down here. So we're going to have negative 1/2 plus or minus, right, that's going to be 6i divided by 2. So we're going to get 3i. Okay. And then so using that, so let's go back. What did we do? Right. So if we got r equals alpha plus or minus beta I, what ended up happening with the alpha and the beta? We ended up taking the alpha and putting it in the exponents of e, and we ended up taking the beta and putting it inside the trig functions. Okay, so we want to go through and just take the alpha, put it in the exponents of e, and take the beta, put it inside the trig functions. And that's the end. That's the or that's the answer. That's all there is to it. Okay. Oh yeah. So for my notes, alpha, beta. Okay, so that's helpful. All right. Let's try another one. All right. So we have 16y double prime minus 8y prime plus 145y equals 0. We also have that y of 0 equals -2 and y prime of 0 equals 1. All right, so first form the characteristic equation. So you get 16r squared minus 8r plus 145 equals 0. And then break out the quadratic formula. So you're going to have 8 plus or minus the square root of 64 minus 4 times 16 times 145 all over 2 times a. That's 32. And we can simplify this. This is 8 plus or minus the square root. And if you just break out a calculator, this is going to be 64 minus 9,280, which is negative 9216 over 32. And so that is going to simplify into 8 plus or minus 96i over 32. And so we get 1/4 plus or minus 3i. Take that, plug it into our formula. So we're going to get C1 e to the 1/4 t cosine 3t plus C2 e to the 1/4 t sine 3t. Okay. And then what is left? Well, we need to go through and use our initial conditions to find C1 and C2. And to do that, plug in 0. If you plug in 0, you're going to get C1 times 1 times 1. So we're going to get C1. And then plus C2 times 1 times 0. So the C2 just drops out. And so we get -2 equals C1. And then to go through and find C2, we need to go through and use the fact that y prime of 0 equals 1. So we need to figure out y prime. To figure out y prime, we need to differentiate these. So we're going to have some product rules here. So I'm going to join these two together, and I'm going to go ahead and plug in -2 at the same time. So we're going to get the first here, which is going to be -2 e to the 1/4 t times the derivative of the second, which is going to be -3 sine 3t. And then plus, then the second, we're going to have cosine 3t. And then again, don't forget that we're plugging in -1/2 here. When we differentiate e to the 1/4 t, we're going to get 1/4. So we're going to have 1/4 times -2. That is going to be -1/2 e to the 1/4 t. Okay. And then next, we need to go through and do the derivative for this second piece. So we'll have the first, which is C2 e to the 1/4 t times the derivative second, which is 3 cosine 3t plus second, not sine 3t times the derivative of the first, which is 1/4 C2 e to the 1/4 t. And then we can plug in y prime of 0. And what's going to happen here? So anywhere there's a sign, you're going to have the terms just going to go away, right? So this guy's going to get killed by that sign term. This guy's going to get killed by that sign term. So we're going to have a term here. So plug in 0. This is going to be 1. This is going to be 1. So we're going to get -1/2. And then here we've got C2 times 1 times 3 times 1. So we're going to get +3 C2. And then if you just take one, y prime of 0, what does it equal? It equals 1. So we're going to get 1 equals negative 1/2 plus 3c2. And then so that's 3/2 equals 3c2. And then so c2 equals 1/2. Pop that in, and we get y equals negative 2 e to the 1/4 t cosine 3t plus 1/2 e to the 1/4 t sine 3t. All right, so there's a second example. And then we can do a third one real quick, just because this situation might be a little confusing. Suppose we have y double prime plus 9y equals 0. We form the characteristic equation. We solve. And hold on, we don't have any alpha. What does that mean? It just means that alpha equals 0. If alpha equals 0, then you're going to have e to the 0t, which is just going to be 1. And so this is going to turn into c1 cosine 3t plus c2 sine 3t. Right? So the e to the alpha part just went away because alpha equals 0. Okay, so that's it for complex roots of the characteristic equation. Thank you for watching. See you next time.